Hi, in this video we are going to build a sales forecasting model using linear regression. So forecasting models are basically of two types. Well, you can use time series analysis for forecasting. You can also use structural modeling or causal modeling for forecasting purpose. Now, what are the differences between these two types of forecasting? Well, in time series forecasting, you forecast the future data by taking help of the historical data. And in other words, you only need the sales data for different time periods, and then you simply extrapolate that to the future. Like in this example, you see you're predicting y value of t from yt minus 1. That means you are predicting yt from its previous period. Okay. So you don't need any independent variables to predict it. All you need is one variable, or it's a univariate analysis wherein you extrapolate the values of historical data to the future. Whereas in the structural model, in structural forecasting or in causal model forecasting, you have this structure of dependent variable and independent variables, or explanatory variable and dependent variable. So y is the dependent variable, and you forecast y from the values of x. Okay, so x here is the independent variable. So that's an regression model wherein you forecast the values of y by using the values of x. So y depends on x. Whereas in the previous case, in the time series forecasting, y used to depend on its previous values in previous time period. So there are two ways of doing forecasting. So in this particular session, I'm going to use the structural way of doing forecasting. Okay, and now this is a type of forecasting which is suitable for cross-section data. Well, what is a cross-section data? If you take data for different entities or different individuals for a fixed time period or for a particular time period, then that will be called as a cross-section data. So let me show you the data. You will be able to understand it properly. So this is a typical case of a cross-section data. Well, we have got data for we have got sales data for different different cities in United States, and we have got attributes, or we have got data for sales in unit, and the competitor price, then the average income in that particular region, the advertisement spending, the average the population in that particular region, and then the price charge for the goods. Remember, we have got the competitor's price as well as the price. So let's not confuse with that. And then the average age of the population, education level of the population, and whether the particular region of in consideration is an urban region or a rural region. Okay. Now this data is taken for different cities or different regions in United States. So each row is one particular region. Okay, and this data is for a particular time period. Okay, say we have got this data from 2000 from the year 2008. Okay, so we call this data as a cross section data, where the data is only for one time period, but it is for different individual or different places. Like in this case, we have got data for different cities of United States. Now this data we are going to use for forecasting purpose. As I've already talked about the definition of the data, so there is a dictionary, you can always refer to it. So the sales is nothing but the unit sales in thousand at each location. Comp price is price charged by the competitors. Income is the community income level. Advertising is budget on advertisement for for a region. Population is the population size of the region. Price is the price charged for products. Age is the average age of the population. Education is the education level of the population. Urban indicator shows whether it's an urban or a rural location. So now the data is clear. We've got most of the data is numeric except the last one, which is the urban indicator, which is yes and no. So in the analysis, we'll transform this particular attribute to a numeric attribute so that it will be easier to use it in the modeling. Okay. Now I have taken I've already taken this data set to my work library in SAS. So let me show you how the data looks like. Well, this is how the data looks like. You can use proc import, or you can directly use from here. You can import this data to the SAS work library, or you can always have your custom library as well. So the first thing that we're going to do is to use the proc contents to see what is there in the data, and just to know the details about the data set. So I'll run the proc content first. Okay, now so let's have the details of this data sets. We've got 9 attributes or 9 variables in total, and out of these 9, I think 8 of them are numeric, and one of them, which is urban, is a character variable. Okay, that's what we expected, and that is what we can see in the SAS data set as well. Okay, now the next thing to do is that let's convert this character variable to a numeric variable. Okay, so that it will be easier for us. Okay, so if urban is yes, then we create an indicator variable urban indicator underscore in equal to 1, else it is 0. So if it is urban, it takes a value of 1, otherwise it's 0. So we are creating this dummy variable first. So let's create this first, and if we go and check, you will see that the dummy variable is created. Okay. The next thing that we are going to do, given that our data set is ready, it's clean enough, we have done the necessary transformation. The next thing to do is to explore the data a bit, just to understand how the data look like. Before even starting to analyze it, before even starting to use it for modeling, it's always good to go with the simple exploration by looking at the descriptive statistic. It does say a lot about, and we'll see how the simple things are going to be useful later in the modeling phase. So first thing I'll do is take the proc means, look at the simple descriptive statistics like mean, median, mode, maximum, minimum, and so on. Okay, so we have got 400 observation in all. The mean cell is 7.5, and the standard deviation is 2.8. And it varies from 0 to 16. That means there are places where there hasn't been any sales. Competitors price, the mean is 124. It varies from 15 to 77, and maximum is 175. So let's look at what is the price of the product. Well, the price varies. Its average value is 115. That means the competitor price is higher on average than the price charged by this particular company. Standard deviation 23, whereas for the competitor case it's 15.3. Now, this gives an indication that the competitor's price is not varying much, or it's not varying much, whereas the price charged by this particular company it's varying a lot, okay, because the standard deviation is more. So the variability or the volatility in the price charged by the particular company in the different regions is more than its competitors. And then we've got the age, education, and the urban indicators. But yeah, in proc means urban indicator will not be very useful. It's a categorical variable. So the next thing that we're going to do is that we have got two segments, right? The urban and the rural segment, right? So how does this values varies with the urban to the rural case? Okay, so let's now sort this data with respect to the urban indicator and then take the proc means again, so that we'll get two tables, each for rural and the urban. Okay, now we have got the proc means values for urban and the rural population, or the rural areas. You can see the sales values, there is slight difference, 7.56 in the rural, 7.46 in urban. Education is 13.8 in urban and 14.03 in rural, which is slightly unexpected, but probably that's the case in United States. People in rural areas study more, it seems. There's a difference in income as well. The urban income is more than the rural income, which is expected, and the advertisement spent, it's more in urban than in rural. So you can see that the expectation that urban or having a segment like urban and rural can actually give you the prediction about the expected sales is somewhat evident by looking at the independent variables here, because most of these variables we are listing out here are going to be used as independent variables in the modeling. So ensuring that there is a variability in the data is always important. Had there been a case where all variables are pretty same to each other, right? The average values or the mean of these variables are same across urban indicator 1 and 0, then we'll be little surprised with this thing, because then there is no variation. Then having two segments like urban and rural is of no use. Then we can instead drop this variable and go ahead with other set of variables. So that's one way of analyzing whether segmentation is proper in this case, or having segmentation as rural and urban, whether it really makes sense or not. Okay, the next thing we're going to do is to check the correlation value. Now correlation says the relation between the different variables, okay, mostly the continuous variables. Of course you can do correlation for categorical variables as well, like urban indicator, but we're not going to do that. It's not much, it's not very important. We'll look at the correlation values for other set of variables. Now why are we looking at the correlation value? That is a different thing, we'll talk about it, but let's do it first. Okay, so this is how the correlation matrix look like. um, you can see that the first value is the actual correlation, and the next one is the p values. Okay, the probability value for significance, whether it's zero or it's non-zero correlation. Okay, so we are not bothered about the significance, just look at the actual correlation values, and you won't find much of a correlation in the entire data set. You go column by column, the maximum is zero point 0.2 here. Here also it's not much. In the third column, not much. Similarly, in the fourth column, and in the entire set, you won't find, much or high correlation. Now the question is, had there been high correlation, will that be an issue? Normally, you might have come across this particular theory on my channel or in other sources, that correlation does create problem, or high correlation does create problem when you build regression models. Well, remember that we are building a forecasting model. That means the purpose of this model is to forecast the dependent variable or forecast the target variable. We are not really concerned about the relationship between dependent and independent variables, or we are not trying to infer anything from the relationship, whether it's a positive relationship, whether it's a negative relationship between the dependent variable and the set of independent variables. There is this is slight different, given that regression models can be used for two purposes. We only care what the prediction is going to be. And the second way of using regression models is use it for finding out the relationship. Okay, say for example, how cells depend on income. Okay, now if income can predict what is going to be the cells, that's also one way of using regression model. If income can tell you whether cells is positive related to income or negative related to income, or if income goes by 1 unit, what will be the corresponding change in sales, well, that is more of inferential model, or model which is used for finding out relationship or infer something from the data. So that is of different type, or second type of kind of using model. Now high correlation is a problem when you are using the second type of analysis, or the inferential analysis. But when it comes to prediction, a fair amount of correlation is acceptable, and you can go ahead with your analysis without worrying much. Okay, there will be some kind of an issue, but that issue can be handled easily later on, so no need to worry about high correlation if you are using predictive model. Okay, the next thing that we will do is to do some visualization plot. So we'll do some scatter plots. We just try to want to see how sales is related to income. Now intuitively sales should actually go up with income. Now let's see, does that reveal in the data? So let's plot it out, and we expect that it should go up, but you can see in the graph, in the chart, it's not really showing. It's still, there is slightly upward trending, but whether that is significant enough, or it's a good enough relationship, the relationship is that clear, it's not very not very clear by looking at this particular chart. But given that we are building a predictive model, a forecasting model, the relationship of this kind is of least important, but it's always good to have your expectation, so that any unexpected later on can always be found out. So that's what you can also do for other set of variables like sales, how sales and advertising are related, how sales and population is related, and so on. I'm not going to continue doing the plots here. You can always try out all possible plots. It's always good to visualize your data before starting to build model. So every time you do something here, you just document it so that it will be easier for you. So we have used this Excel sheet wherein we have taken the data from. So we can use one of these tabs to save your results so that you can always go back and see what analysis did you do and so on. The next thing we'll do is and this is something that is used or is this practice is an industry best practice where you build a model in one type of data and then test it out in another type of data and then finalize your model. Or in technical language, you create training data set and test data set, build your model in training data set and test your model in test data set, and select the best model in test data set, not in training data set, and then deploy your model. So that's what we are going to do. So what is the logic behind it? Why is this done? Well, the fact is that your model that we're building is not going to be used in the same data set. It is going to be used for new data set. Well, for the same data set, we already know what the sales values are. But for the new data set, we are going to use this model to know their values, right? But we don't have the new data yet. So what instead we do is that we create a hypothetical new data. So how do we create that? We take a percentage of our historical data and keep it aside. We don't use that particular data set for using in the model. We create a separate data set for building model and keep the rest of the data for testing purpose. So training and testing data are mutually exclusive. That means if a data point is present in training data, that will not be there in test data, and vice versa. Okay. So how are you going to create these two data sets? We are going to use proc survey select because we are going to select randomly to ensure that it's not biased. Given that in this particular situation it's not going to matter much, but yes, it's always good to go with some random selection algorithm which is going to give you unbiased selection and ensure that proper distribution is there in training and testing. And that's important. The training and testing data should be similar. Okay, they should not be highly dissimilar. So instead of choosing data by yourself, it's always give it to the algorithm to choose randomly for you, so that it's going to be less biased. Or so the syntax is like this. We're going to use the parent data cells, and the methodology uses the simple random sampling. The sample rate is 0.7. That means 70% of the data is going to be used for training. That means we are going to use 70% of the data for building model, and the rest data, which is the less 30%, is going to be used for test data, in the test data or while testing the model. You use the syntax out all and use the keyword out just to save in another data set, so that both training and testing will be identified, and then you can take it in different data set later on. So let's run it. It will be more clear. So let's run this code and let's see what is there in cells 1. Okay, so let me go to my work library. Well, cells 1 is the out data set in this case. Now there is a select indicator in this case. Now it's 1 and 0. So every time it's 1, then that particular row is going to be there in the training data set, and if it is 0, then the data point or the row is going to be in the test data set. Okay, so that's the logic in this case. Okay, now given that it's there in the same data set, but we need two data sets, right? So we subset it. We subset by using the if condition. Selected is equal to 1, then it's cells underscore trend. So we create two data set from this particular data, and then we also create the test data set if selected is 0. Okay, so that's what we have seen, right? So in total we have got 400 we used to have. So 280 observations are going to be there in the training data set, and the rest 120 observations will be there in the test data set. Okay, now that we have done bit of analysis and our data set is ready, we have got the training and test data set. So let's start with the model development. Now you might wonder that this is too early for model development. We haven't even checked the distribution of variables. We haven't seen whether variables are, there is a bit of a multicollinear, expectation of multicollinearity or heteroscedasticity in the data. Well, if you're building a forecasting model using linear regression, you need not worry much about the different assumption of linear regression. In strict sense, I'm not saying it's totally immaterial or totally not very important, but it's not strictly very important, because you are going to validate your model anyway. So, and all you really matter, all that is that's matter to you is how well your model able to how well your model is able to predict your dependent variable. You don't really care much about the other things. You are not going to explain this, or you're not going to draw conclusion from this model. You're not going to use this model for policy related purpose. Had that been the policy related objective had been there, you probably will be worrying about the different assumption in linear regression, because that's what because then you will be interpreting the signs of the estimates, you will be interpreting the p values, t values, and so on, and then this assumption have to be made. Otherwise these things will not make any sense. But in forecasting, straight away you can go for building a model without worrying much. But once you have done the model building, ensure that you test it well before deploying it, and we will see how we do that. So the first thing is, go with this very simple modeling structure. We don't know whether it's going to be correct, but let's start with this. We'll use proc regression because it's a multiple linear regression analysis. You can use proc GLM as well, but I'm going with proc reg. And we'll do the model building exercise on training data set. Remember, it has only 280 observations, so we have left out 120 observations here. So it's not the first data set we looked at, it is a subset of that. And then whatever comes out of this regression, will save it in out test in a different data set. So the model statistics are going to be saved in particular way. So our model look like this. The dependent variable is of course cell, because we are trying to forecast cells. So cells is the dependent variable, and there are several independent variables: the competitor price, income, advertising, population, price, age, the education level, urban indicator. There are 8 independent variables in all, and let's run this regression first. And remember, this is the simplest form of regression. We haven't done any exercise. So by looking at the simplest form, we'll get to know Okay, let me close this first. Okay. Now this is how the regression output look like. The R square values and the adjusted R square values are 0.52 and 0.51 respectively. Okay, very close. They're very close. R square and R square are very close, and 51% is it's decent enough. Okay, but whether it can be increased further, something we'll be interested to see. Now there are two things which are important to look at and very important to look at if you're building a forecasting model. Even before going to parameter estimate, that's of least importance in forecasting model. Two things are important. One is R square, the other one is the root mean square values. So the root mean square error value should be as minimum as it possibly can, and the R square value should be should be should be a good value. Okay, and the more it is better. Similarly, the adjusted R square should also be high, should be very high. Okay, now let's see how the parameter estimate look like. Well, if you look at the parameter estimates, although as I've already said in the beginning that we're not really interested in the signs of the estimate, and we're not interested in the significance of these variables. But if there's there are too many insignificant variables and the signs are not as expected, then you might expect a bit of um, you know the estimates not to be or the numbers not to be um, there will be a variability actually. It's not going to be robust enough. So it's always good to check these values even though you are building a forecasting model, although a little bit of here and there is not going to affect your model much, but too many issues with your estimates, a reason for worry. So let's see. So with competitor price, it's positive, expected. More the competitor price, well, it's not expected, right? So that's something that is unexpected sign. With higher income, higher sell, expected. With competitor price, that's right, that's not an unexpected sign, it's expected sign, because more the competitor price, you will expect the company's product to sell figure to go up, right? Because competitors is selling at a higher price. Income, expected sign. Advertisement, more advertisement budget, more is the sell, something that is expected. With population, there is a wrong sign, but again it's not a significant one because the p-value is 0.6, so we cannot really interpret that, so leave it there. With price, higher price, less sell, expected, negative sign, perfect. And then age, more the age, less sell, which is expected because young people, maybe this product is electronic product, young people tend to buy more, so that is expected. Higher education, less sell. So maybe some products, higher education people, they know more about this product and they don't really want to buy. Maybe an Apple phone, people know who it sometimes it's seen that educated people don't really buy expensive product, like an iPad or iPhone or something like that. So and so it could be a reason. So we're not sure how education really affects sales figures, so that's an ambiguous sign again. Then urban indicator. So in urban there is higher sale, but then it's not, again it's not significant, so can't interpret. So education and urban indicator both again are insignificant because of the p-values are very high. So we're not going to interpret this two, but the two values. So my explanation of how education and affect your sale and it's related to sale, I take it back because I didn't see the p values first. So I'm sorry. Okay. Now that we know bit about how the variables are related to the dependent variable, which is the simplest form of model, let's ensure that the predictive power is more. We have 52% R square. So let's try a little bit and to ensure that it goes off. Okay, that will be better. Moreover, what really what really is important at this point in time is see which of these variables are insignificant. Well, there are three variables which are insignificant. One is the population, the next one is education, and the third one is urban, or the urban indicator, right? So um, now what happens is that sometime there exists nonlinear relationship or a polynomial relationship between dependent and the independent variable. We have used only the linear relationship. That means we have not used, or we have not taken the higher degrees of or any polynomial form of any of these independent variables, right? So maybe we can also try this thing, or maybe we can take a logarithmic transformation of these variables and use that in the model instead of using simple. That means instead of population, we can use a square of population or logarithm of population. Similarly, instead of using education, we can take the square of education or logarithm of that, and you see whether that comes out to be significant. And it is always expected that if a variable is significant, most likely it's going to increase the predictive power of the model. So indirectly, significant variables are helping us building a good forecasting model. So let's try that out. So we have done with model 1, that's the first form of model. The next one is the model 2. Now why I'm trying to name these models, because later point of time we are going to compare with some indicators values or with some statistics, and we'll see which one is the best one. So we have seen the first form of model, first version of model. The next thing we're going to do is that create two additional variables by squaring education and squaring population. So now we have education underscore SQ and population underscore SQ. That means we have simply taken the square of education and square of population, right, and created two new variables. And then we use these two variables in this this model, and let's see whether it has an impact in the model. Okay, all right. So let's look at first the R square value. Well, it seems the R square value hasn't really changed much. Okay. Have we? Okay, I think this is the old result. So let me run it again. I think. Okay, I'm really sorry because I haven't run this code. So I should run this code because this is not created. Okay, perfect. Okay, let me run this second model. Okay, now the R square value seem to be pretty same, or maybe very slightly increase in R square value. R square, adjusted R square seem to be exactly same. There is absolutely no change. And what about the significance level? Well, you can see The population is now tend to be a little more significant, but not significant yet, although the p-value has come down drastically. Similarly, education hasn't really been significant. That means the quadratic terms hasn't really contributed much to the model. Okay, that's what is the conclusion. Now, by adding this additional variable, has it increased the predictive power? Well, from root mean square values, from the R square value, it doesn't quite tell us that that the predictive power of the model has really gone up or not. We can't say that by looking at these values. But then root mean square values and the R square values are not the ones which are going to give us the confidence that the predictive power of the model is good. The question is why? Well, we all know R square matter a lot. Well, it does matter a lot. But the problem is that we are building the model on training data. And training data is already a realized data. This model is going to be used in a new environment, and there what matters is whether in the new data the model is performing well. So we're going to check the model statistics in the test data, and remember we are only working with training data so far. So even though these values like root mean square error and R square values in the training data set give us an indication of the predictive power of the model, it doesn't quite give us that full confidence that it's going to work or not. So it's just an indicator, right? And finally we'll compare the statistics in the test data set and select the best model, and that's going to come later on. Okay, so for now we're not we're not jumping into conclusion, but yes, it seems that by adding these two extra variables, it hasn't really increased the predictive power much. The next thing we were going to do is that why not be a little more flexible? After all, we are doing a forecasting model. So if you're doing a forecasting model, you can be a little more flexible. That means you can take as many transformational variables as you possibly can. So instead of using transformation only on two independent variables, we have done transformation. We have taken square and taken cubes for a number of independent variables. So I've got education square, education cube, education log, that means logarithm of education, and then population square, logarithm of population, and then I've also taken square values for the competitor price, income, and advertising, and so on. Now one might question me that, well, taking the square of education or cube of education population is fine because these variables are insignificant variables. But why have we transformed, or why have we taken transformation of variables which are already significant in the model? Well, that's fine, but you can always take transformation of even the significant variable, use that in the model, and see whether that contributes to predictive power of the model. Well, it may not give us, it may not be very useful, or in fact it looks very stupid if you're using this model for policy related purpose, like for inference or trying to see the relationship among the variables. But when it comes to forecasting, every bit of increase in R square, or every bit of increase in predictive power of the model is always good. Okay, so try it out, have as many number of transform variables and use that in the model. Some people argue that computational issue is going to be there. Well, now with given in the current in the scenario, I mean in the present days, we never face computational issues because computers are very efficient nowadays, right? So we're going to use this transform, all these transform variable in the model, and let's see. I'm curious. I'm not expecting much, but still, we can it might so happen that by adding more number of variables, the predictive power might have gone down as well, right? And we don't know. So let's see. Well, the r square values, uh, the r square values is again, has it run well? Okay, I'm sorry again, I haven't run the data set first. The transformation has to be run first. Okay, now I'll run this particular code first, because in the data step we are going to transform these variables and then we can use them. Otherwise, it's going to show the error. So now I'll run the regression code. Okay, now the r square is 54%, so it has gone up by 2%, but the adjusted r square is pretty much same. It's again 51%. That means, so what is the difference here? Well, the difference is that although the r square has gone up by 2%, the adjusted r square hasn't really gone up. So which one of these matter to us more? Well, it's the adjusted r square that matters to us more than the r square. Why? Because it penalizes for adding more number of attributes. Now question is, can we say that the predictive power of the model hasn't really gone up? Well, we cannot say anything by looking at the r square value. Actually, r square value only gives us an indication. We'll have to look at the mean square error to be able to judge the predictive power of the model, and that we do not have at this moment. So looking at the root mean square error in training data set and having a good r square value doesn't guarantee good mean square error in the test data set, and that's what matter to us, whether it performs well in the test data set or not. So here is an interesting result that it has really helped us increasing r square. So let's see whether it has really performed well in the test data as well or not. And you might be surprised that it doesn't guarantee that, or you might come across, you might see a completely different result in test data set also. I'm also curious how it turns out to be in the test data set. Okay, now the last type, the fourth type of model that we're going to do is that now that we have so many independent variables, we can use some variable selection criteria. Now you might have come across this variable selection criteria in number of models. If you have seen one of my case study on churn analysis, I have used the selection criteria, variable selection criteria like forward selection, backward selection, or stepwise selection. So people who are not aware of these things, well, the variable selection criteria is nothing but it's an automated algorithm which finds out the best set of independent variables which really are so important, are very important for the model, and by using this best set of independent variable you can achieve good predictive power. You build a good model, good predictive model. So the purpose is to reduce the number of variables and only get down to few or a best set of independent variables. And what is the reason why do we do that? Because we always want a small number of variables, right? And that's important. Sometimes by having too many variables also decrease the predictive power of model. Okay, I'm not going to go to the theory of why it is so, but yes, I have this experience that where having more number of variables has really brought down the predictive power. And again, when I say predictive power, it's on the test data set. So in the new data set, things have to be very stable, otherwise it's not a good model. So let's run the stepwise regression. Okay, so the stepwise regression, it drops values based on variables based on certain criteria. If you look at the output, it says that variables which did not meet the significance criteria at 0.15, so values, p values, anything less greater than 0.15, they have been dropped from the model, haven't been able to enter into the model. So the variable has to have this particular threshold p value to be able to enter into the model. So only 5 out of so many number of independent variables, I guess 14 independent variables including the transformed ones, made it to the final list of significant variables or important variables in the stepwise selection. So what are these? Price, competitor price. See, now this is an interesting thing. We have got price and competitor price, but instead of age we have age square. That means quadratic variable age is more important to the model than the age. Okay, the linear age or the first degree age. Similarly, income has also, the quadratic variable is more important. That's why it's in the model, it's more significant. But earlier, if you see income without even the square variable, it used to be significant, but it's no more important now. So that's why I said in the beginning that it's always good to go with some transform variables, include them in the model. Probably even though the same variable was significant before, it still could give you very interesting results. What about the R square and mean square error and so on? It doesn't give you here, but let's move on, because that doesn't matter to us much. We'll see that in the test data set, and that's where we compare the predictive power of all these 4 types of model that we have built. Now before doing this model selection, we are going to use the cells test data set in this case. Now remember, we haven't done the transformation in the cells test data set. So first thing we'll do is to do all the transformation. Okay, so whatever transformation we have done with the cell training data set, we'll also use that for the test data set, right? Square, log, and cube, and so on. Okay, now in the test data set, I remember what is test data set. We have taken 120 observations from the parent data set and created a test data set. Now this data set is not part of training, right? So please be not confused in this. Okay, now this 120 observation are going to be predicted. Okay, and we are going to predict the cells values of this. So we'll use the proc score from the SAS procedure. Is a SAS procedure. We can use it for scoring purpose. Scoring is nothing but using your model statistics. That means whatever estimates that you have got to to do the or to score your dependent variable. So technically it's known as score. That means you have the equation, just find out the dependent variable. Now somebody might ask me, well, we already have the dependent variable values. Well, we actually know the dependent variable values for even the test data set, but we'll compare that later on. Let's first predict it by using the test statistics. So I'm assuming that you have the background of or theoretical knowledge of linear regression, so that you should not be confused. Otherwise, just watch my video on linear regression, you will be able to understand it better. So we'll use the model number 1 and score the data. So the syntax is like this: proc score dataset. We use the trace dataset here, and then we take the output statistic what we had saved initially, right? Remember we had saved something in out test, right, in all models. So that means the model statistics what we have seen in output are saved in one particular data which is going to be used for squaring. Okay, and then we are saving it in out data set pred. Okay, and then whatever number of independent variables we use in the model, we need to use these variables in the var statement. Okay, because otherwise how will the algorithm know that okay, these are the variables I'm going to use for scoring purpose. So we have the scoring data, we have the scoring statistics, and we'll get the score. Score is nothing but the cells values or the forecasted cells value. Okay, and the next thing that we'll do after doing this, let's first run this and then we'll go to the next. Okay, so let me run this. Okay, it's run fine. So let's see what is there in the pred data set. If you look at, okay, some issues. So there must be some error. Okay, education and population not there. Okay, there's something wrong here. That means these variables are not part of in the first model. So you need to do a cross check. 1 2 3 4 5 6 7 8. Okay, so 8 variables were there in the first model, so we're going to use the same 8 variables, otherwise it's going to show error. Now it's fine. Let's go to the pred and see what is happening. Okay, the last variable is the new one. It wasn't there before. Okay, now this is model 1. Okay, that means the name of the variable is model 1. Don't confuse with the actual model that we have built. It just is a name given by the algorithm. Okay, now we have this forecast values and we have the actual value as well. So where is our actual value? The actual value is nothing but the cells. So where is cells in this case? Here is the one. Okay, now look at the first row. The first row, the actual cell value for testing data set in the testing data set is 10.81, whereas the model values or the forecasting value using the model that we have built is 11.69. That means there is a difference, or there is a difference of 1 point. So in the second case, the forecasted values of forecasted cell is 8.79, whereas the actual cell is 12. That means that there is a difference of 3 or 4 unit, and so on. That means the model does good, and sometimes it doesn't do good number of times. So how do we measure? Is there a statistic which really says whether the model is doing well? Well, we can aggregate this by using what is known as the mean square error. So we'll use the mean square error. You can also use root mean square error as well. They're similar. So I'm going to use this dataset pred. So I'll calculate the mean square error. So mean square error calculation is very simple. That means you subtract the actual you subtract the forecast from the actual, or otherwise it doesn't matter because you are going to square it. So actual cell minus the forecasted value, so that's the difference. I have already shown you the difference. Square it because it's going to be negative, positive, so it's good to square it first. So that's mean square, or the difference, square of the difference, and divided by the total number of observations. So total number of observation is 120 here, so divided by that number. And then we're going to take the sum of that, okay, sum of that values. Okay, so summation of that. So since I cannot do summation in this particular equation, I have used proc means in the next step. So please don't confuse with that. The root mean square actually is a summation of that. So there is a slight it's a little bit of wrong. The formula is a little wrong. That means the summation sign is missing, but I am summing it up in the next step, so doesn't matter. Okay, now I have run the scoring value. Let me find out what is the root mean square value. The root mean square value is 3.18. Okay, so now I'm going to take it to the Excel sheet, and so it's 3.18. So it is 3.18 for model 1. I'll repeat the same steps. I hope you have understood now. So I'm not going to take you through the details. So I'll repeat for model 2, model 3 and model 4. So I've written the code. Syntax is same, proc score, and put all your variables, whatever you had used in the development of the model. So you have to change the variables, like, I had 8 variables in the first model, but I've got more number of variables in the second model. So okay, the second model, okay, the second model had two extra variables, right? So the two extra variables were education and population square, right? No, nothing else, right? More than that. So I'll use the same code, except that I'm going to add 2 more variables in the scoring list, and I want to see what is the mean square again. Okay, and I'm going to use out start 2. So remember to change that. Okay, out start 2. .13. So better. So for model 2, the root mean square error is 3.13. Okay, then we'll go to the model 3. We'll use out start 3 from output model 3, and then we'll also put all the independent variable that we had used while developing the model. So all transform variables, we had so many variables in this case, and let me see what is the mean square in this case. 3.48. Now this is interesting, isn't it? Remember, when we use all these 14 variables in the model, the R square value had gone up, and also we had seen the R square values going up by 2%. So we used to think that at that time we thought that probably the predictive power has really gone up by adding this extra number of variables. But now look at the root mean square value. It has actually gone up. Ideally, we expect that for a good predictive model, the root mean square value or the mean square error should be minimum. But it is, out of these 3 models so far we have seen, this is the maximum. We are expecting it to be the minimum, but now it is it is different. It is something that was not expected. Now this is the irony, that even if the model works fine in the training data, it might not work fine in the test data set. And what matters to us more is if the model works in the test data set, and here it doesn't work. So never be confident by looking at the statistic in the training data sets. It can give you misleading results or misleading conclusion. So now finally, let's see how the model 4 turns out to be. So using model 4, in model 4 we use the stepwise selection criteria, and 5 variables were finally selected. So we'll score this test data set using these 5 variables, right? Like price, income square, age square, and all. Okay, and let's compute what is the mean square error in this case. Yes, now this is 3.14. Now this is an interesting analysis. Very less number of independent variable, but look at the mean square error. It's much less than what we had in the second model, where we use 14-15 independent variables. That means more number of variables need not necessarily ensure a good model. So now that we have the the mean square error in place, now we need to select which one is the best model. So out of the 4 models that we have seen so far, we have listed out the p-value, that means the number of independent variables used in the model, and the corresponding mean square error. Okay, in the first case, 8 independent variables used, mean square error is 3.18. Next one is 10. Then in model 3 we use 17. Model 4 we use 5 variables. And the least one comes out in model 2, where we have 3.13 mean square error. And remember, the minimum the least square error is the minimum the mean square error is, the better is the model. More predictive power is there in the model. Okay, so ideally we should be choosing model 2, but model 4 is also very close to model 2. See, because it's only 3.14, there is a difference of 0.01. And look at the difference in the number of independent variables. So in the model 4 we have only 5 independent variables, where in model 2 we have 10. That means the number of variables is almost half. So we always want a model with less number of variables, because it's easy to implement, and moreover the model statistics are going to be more stable. Okay, otherwise more number of variables means more uncertainty with the model, more instability with the model statistics. So ideally in this case, although it's not it's not improper to go with model 2, but ideally one would expect that we go ahead with model 4, because it is giving us good predictive power. At the same time, there are less number of independent variables involved in this. So we'll go ahead with model 4 in this case. Okay, so we have now built a forecasting model. We have seen that this works well. We have taken 4 cases, 4 different modeling scenarios, but it can be extended to a number of cases. And I encourage you to think about how we can build more number of models and compare. So I'll give some food for thought. So what you can do is that I'm not going to do it, but yes, if you're interested, you can always try these things out. So take more transformations. Okay, that could be one thing. Use selection criteria like forward selection criteria, backward selection criteria. So build models like that. Also use subset selection. That also you can use and see you can come up with a number of models. Then you also use other type of algorithms. So why use a linear regression, right? You can all use non-parametric form of regression, right? Spline regression, and so on. And see because for all regression, the good thing about the mean square error is that you can always get mean square error from, it doesn't matter what kind of regression you do, you will always get that value because you are directly computing using formula. So you're not getting directly from regression method, so don't worry that it's not going to be there in the output. So you can easily compare these models and see which one is the best. So ideally you start with 10-15 models and forecasting models and choose the one which is best in terms of the mean square error. So I encourage you to try that out. Now that the model is built, we need to deploy that in the production, right? So ideally how this model is going to be used in a project, in analytics project, it's going to be different because IT is going to take that model and use it in systems, and a lot of things happen actually. But I'll just give a very brief overview, and it need not be the same in actual project, but those who have never worked in analytics project will get a feel of how models are actually used in actual scenario. So now that we have the numbers, all we want is the 5 statistics or 5 estimates, slope estimates, and the intercept estimate from the regression model. Right? So that is saved in the out test data or out start data, out start 4, right? Because last model is the one we have finalized to be used, right? Now in a new setup, how is going to be used? In new setup, you are not going to have sales value. You will only have the values which are known to you. Now price is known to you, right? Because company sets the price, so it knows the price. Company knows what is the competitor's price, that's also known. Average income of the location is already known, right? You can always find the company can find it out beforehand. The advertising expenditure is in the control of the company, so the company knows it beforehand. Average age of the location, in the location, that's also is something that you can find it out, right? And in fact you don't need to find that out again and again, because once you do that you can always averages can be easily found out for the next period as well. Now these are values before even before the period, you can always get these numbers, right? Or else if the forecasting can be done for 2 things here. Okay, let me clarify this here, and it's an important point. One thing, for different time period for the same location, okay, same location, okay, the location we have already seen, but different time period, okay, that's also for that region we can use this model. Or else we can use this model for completely different location, that means a totally new location, okay, new location or new place, okay, because all we need is this 5 values. If you have that, we can use it for different period, different location, doesn't matter. So first you get these values in a data set and then use the transformation, because raw values will not have the transform variable. So because the model has some transformation, right? Square, income square and age square. So when you collect data, you don't get in square forms, in quadratic form. So you change, transform that variable. And the next one is use proc score, or else you can simply write a data statement, and use these numbers, the statistics numbers you have got in the model, and find the score. Or else use proc score. Proc score directly finds, gives you the score without taking in direct, making the calculation. You can avoid the calculation, you can use proc score and it's going to give you. So let's run this and you will get a feel of how this scoring is done. So I'm finally printing the forecasted sales value, and that's what matter to the sales people. Remember that whatever we are doing, the numbers are not going to be understood by the sales people. What they will understand is what exactly is the forecasting value. They want that final number. So here is the final number. Okay, so the sales forecast for, say, for the next two new places, new place 1 and 2, are 9.03 and 7.26 respectively. So these are the two numbers that matter to the business most, and based on that some decision is going to be taken, or maybe some. So how are they going to, how does it really matter to business? So let's talk a little bit about how does it matter to business. Well, will the business think that, okay, this forecasting, well, the sales forecast is 9.03, will they remain silent? No. If they want the forecast values to go up, they will invest more on advertising, because they know that it has a positive relationship. So if they increase it more, it's going to, the sales value is going to go up. Okay, now after knowing that it's going to be 9, they think that the first region, the advertising expenditure should be more, so they increase this value. So instead of 15, they made it 20. Instead of 0, in the next case, they made it 10. Now let's see how the forecast value change. Now you can see it has gone up. That means the sale has gone from 9.0 to 9.75. Similarly, in the second place as well, in the second location, the the forecast value has gone up. So some of these variables are within the control of the company. That means the average income of people is not in the control of the company. Similarly, the average age of the people, average age of the population is not in the control of the company, right? And similarly, competitor price is also not in the control of the company. There are two important variables which are within the control of the company, right? One is price set by the company. So if it can bring down the price. The second thing is the advertisement. It can spend more on advertisement. So price and advertisement are the two decision variables which are going to be used for ensuring that the forecast value go up more. Okay, so that's how you build a forecasting model. I have shown you a very simple forecasting model. Of course, in real scenario, you will find a more complicated one. So to get the dataset code that I have used, so visit our website. You can find the link to our website in the description section. Visit the website, download the data, take the code, practice it on your own. Write to us. You can also find our email ID. Write to us how the session was, and you can also ask us more session like this. You can always request us. Thank you so much.